The foundation of calculus, the study of change, is the concept of limits. The goal of this video is to introduce what limits are, how they can be useful, and how they are evaluated. Many functions have what one could consider imperfections. Not that they are innately bad or terrible properties, but that they can be tricky to manipulate or formally discuss. These can come in the form of vertical asymptotes or horizontal asymptotes. These can also be singular holes present in the graph, or they can be jumps between two different values on a graph, just to name a few. So how can we mathematically talk about what is going on around a specific point without worrying about any missing graph or wacky behavior? This is where limits can help us out. Limits are used when we want to approach or go to some value without necessarily reaching it. In the context of graphed functions, limits do not attempt to find the defined value of a function at a horizontal position. Instead, limits seek to answer what a function appears to approach as our input gets closer to a value. Let's dive into a concrete example. Consider the graph of y equals absolute value of x. If we wanted to see how this function behaves around x equals -2, we can ask what the limit of absolute value of x is as x approaches -2. Mathematically, we would write this limit as lim, absolute value of x arrow -2. This is read as the limit of absolute value of x as x approaches -2. Obviously, limits don't spit out a paragraph description of our graph at a point. Instead, limits provide us with a single number that represents what value the function approaches as its input goes to a value. Now if we go back to our function, we can see that as the input x gets closer to -2, the function approaches 2. So, the limit of absolute value of x as x goes to -2 equals 2. We just answered the question, what is happening around x equals -2, by stating that the limit equals 2. Now, what if there was a hole at x equals -2? First off, we'll call this new function f of x. If we track what happens as our input approaches -2 on the graph, we can see that we get the same answer, 2. It's important to realize that limits do not determine the defined value of a function at a given point. They determine what the function is approaching. So even if f was defined at x equals -2, we would still get the same exact answer no matter where it is defined as. The important part here is the surroundings, not the actual point itself. So we can actually completely cover up that portion of the graph and still compute a limit. Let's examine this notation. If we were to read what this says, it would read, the limit of f of x as x approaches a equals L. Now let's look at the notation showing that x approaches a. With this notation, limits are evaluated as the variable approaches a value from both sides. Imagine a number line at some number a. If we look at the statement x approaches a, this would mean that x is approaching a from both the left and the right. If we add a superscript to the value we are approaching, we can specify which direction we want to approach it from. Adding a plus indicates that we are approaching a from values greater than it. On a number line or on an axis of a graph, this is typically from the right side. Adding a minus indicates that we are approaching a from values less than it. On a number line or on an axis of a graph, this is typically from the left side. This is especially important when we want to compute limits of functions like this one. Let's first evaluate the limit of this function f of x as x approaches 1 from values less than it, i.e. the negative direction. If we follow this bottom circle along the graph, we arrive at y equals 0. So our left side limit of this function at x equals 1 is 0. Now, Let's evaluate this limit from values greater than 1, the positive direction. If we follow the bottom circle along the graph, we arrive at y equals 2. So our right-sided limit of f of x is equal to 2. Notice that we used the same graph, but we approached two different values because we approached one from different sides. Now let's try to evaluate the limit without specifying a side. If we follow the bottom circles along the graph from both sides, we arrive at two different values. The left side limit gives us a value of 0. The right side limit gives us a value of 2. But what is our answer then? Is it 0 or is it 2? In this case, we would say that the limit does not exist, or DNE for short. Note that this does not mean the limit equals the word does not exist. This is purely notation for the absence of a limit and is not actually a number. This conclusion allows us to state the condition for a limit to exist. We say that a limit exists if the right-sided limit exists, the left-sided limit exists, and they are equal. Let's examine a few more scenarios where the limit may not exist. What if we wanted to evaluate the limit of square root of x as x approaches 0? Since we didn't specify a direction, we are approaching 0 from values above and below 0. If we follow the bottom circles, we get a right-side limit of 0, but what about the left-side limit? We cannot evaluate a left-side limit at x equals 0 since there is no graph on that side. If there were, we could have easily done so. Since this left-side limit does not exist, the entire limit must not exist. Now let's consider the graph y equals 1 over x plus 2. This graph contains a vertical asymptote at x equals 0. Let's attempt to compute the limit at x equals 0. If we follow the bottom circles along the graph from the right, we don't actually get a specific value. So we could say DNE for this limit, but we can be more specific. Since our graph goes up forever on this side of 0, we can say the right-sided limit equals positive infinity. If your graph endlessly increases and never approaches a single value, then it is approaching positive infinity. Now if we evaluate the left-sided limit, we end up going in the opposite direction. Once again, we don't end up approaching a value. We just keep decreasing forever. So this limit also does not exist. We can also say that this limit goes to negative infinity, since our graph keeps decreasing forever and never approaches a single value. Now if we compare our limits, we can notice that they are definitely not equal. So we can safely conclude that this limit does not exist. If both one-sided limits go to the same infinity, we can be more specific with our final answer. Consider the limit of 1 over x squared plus 2 as x approaches 0. If we approach x equals 0 along the graph from both sides, they both approach positive infinity. So we can actually state that our limit is equal to positive infinity. The same logic would be applied if they both approached negative infinity. Finally, let's examine this wacky function. The graph of y equals 5 over 2 minus 1/2 sine of 1 over x. As we approach x equals 0 from both sides along the graph, we approach 2? Wait, no. 3? No, that can't be right. 2.5? This is very frightening and I don't want to be here. So we actually can't determine what we're approaching here. This sine of 1 over x is actually rapidly oscillating between -1 and 1. The 1 over x simply keeps increasing since we are dividing by smaller and smaller numbers as x approaches 0. As a result, we are unable to determine what this function approaches as x approaches 0. So this limit does not exist. The same logic applies to any function that endlessly oscillates between two values forever. This includes trying to determine what cosine approaches as our input grows infinitely. Can you see what value we're approaching on here?